So thank you all and welcome to Strait Science. Strait Science is a evening presentation series, science series put on by UAF Northwest Campus here in Nome, University of Alaska Fairbanks Northwest Campus here in Nome, and also University of Alaska Fairbanks Alaska Sea Grant. That's me, and you're joining me in the home office, which it sounds like for Alaskans, if you're state employees, it looks like you might want to check the news tomorrow. It looks like we'll be working from home next week, given the COVID situation. Regardless, welcome. Tonight, we're really excited to have Craig Lee talk to us about a lot of the technology that's headed north and also some of what they have learned and are planning on learning. So Craig Lee is the senior principal oceanographer at the University of Washington Applied Physics Lab. And he is no stranger to SIKULIAQ, and he will be, you'll see SIKULIAQ coming into the dock around the 30th. They'll be busy down there, and they certainly don't want anyone coming by, especially with the COVID situation. And right around the first part of October, Craig Lee and his research party will be coming out to Nome and getting on the ship. And we hopefully won't see them around town, and they don't want to be, not unfriendly, but they don't want to be exposed to anything that they may take with them on the ship. So it's good, and we're really grateful. Craig's going to tell us what's happening and what's going on with the cruise as he goes north. With that, take it away, Craig. We're interested to hear about the ice, the ocean, and the technology that's headed north, and how the Naval Research Program fits in with this. Thank you so much.
Great, thank you, Gay. And thank you everybody for tuning in. I appreciate everybody taking time out of the evening to listen to me share what we've got from the Office of Naval Research Programs. I've actually been looking forward to doing one of these for a while, and I'm sorry that I can't be there in person, or I will be there in person, but the circumstances aren't such that we can do an in-person gathering. And as Gay said, please do excuse us. We'll be up there in about a week, 10 days, but probably trying to make ourselves pretty scarce. In another day, we'll be in and out for some years to come. But tonight, what I wanted to talk about was really the arc of a number of Office of Naval Research programs that began with ONR's return to the Arctic almost a decade ago at this point. It was the start of that, and it has extended to the present time. A mix of both science and a lot of technology development in pursuit of Arctic observing. The work I'm going to talk about tonight is the work of a lot of people, as anything that's this big. I'm kind of the person talking to you tonight, but the people responsible, you'll see their names on a lot of these slides. Huge teams of people in the marginalized zone, sea state, stratified ocean dynamics, and Arctic mobile observatory system programs, each of which is 3 dozen people or so working on the science. So let's see if I can get the there we go. For those on the phone, what I'm showing right now is a slide that just shows interconnections between different parts of the Earth system. And because I'm an oceanographer, the ocean is at the center because, of course, it's the center of everything. But really, kidding aside, there are many connections with changes that are happening in the ocean that extend out to the atmosphere, to global climate, to ecology, both marine ecology, the Arctic, and further downstream in subpolar regions, to the terrestrial system, and to the human system, right? Both due to greater access to natural resources or loss of some natural resources in terms of food resources, increased storm hazards, various things that have significant human impacts. But fundamentally, these things have to do with the fact that we're seeing more open water, right? It's getting a little fresher, it's getting somewhat warmer. The ice is starting to go away, right? And we'll talk about more of those things in a minute. But the idea here was just, it's something that people in this area are experiencing, so I don't really need to tell you this, but the impacts are many, and they extend out to lots of different systems. And this is all to motivate why we make these observations, why we're so worried about this. So the slide that I'm showing right now has on the top sea ice extent for March, June, September, and December 1980, and then a similar plot for 2019. And the point here is that if you look at 1980, and if you look at the thin red line that outlines the sea ice extent, which is the median sea ice edge from 81 to 2010 for this region, you see that the region's ice covered pretty much year round. September, the sea ice minimum. Sea ice shrinks away from the Alaskan coast and away from the Canadian coast, but it's still there. It's still present in large quantity. Leap ahead to 2019, and in particular, as you come into June, September, right, sea ice is pulled way back. Lots of open water in the Canadian Arctic, Alaska region. That has a number of different implications in terms of ecosystems, in terms of the kind of coastal erosion you might see due to wave action. Right, Jim Thompson has been up recently and has a project looking at the impact of the surface waves on fast ice on the coast. That story is more than just extent, though. That story extends to the kind of ice and the thickness of the ice, the quality of it. What you see here is plotted in a time series plot from 1999 to 2015, a number of little postage stamp size images of essentially percentage of multi-year ice, where red indicates lots of multi-year ice and blue indicates no multi-year ice. And what you see is that earlier, right, turn of the century, lots of the Arctic, in particular the area north of Greenland and north of Canada, is covered with thick multi-year ice, and it extends out into the central Arctic. But as we come to the current time, and we were really six years, the spot needs updating, right? It's 6 years old at this point where it ends. But that extent of multi-year ice is really peeled back just to the area around Greenland and the Canadian Arctic archipelago. And the rest of it is largely dominated by thin first year ice. So it's really, right, extent and thickness is sea ice volume, but it's also the quality of that sea ice that affects any issues of how it evolves and what happens with it. The ice season has been changing as well, and this is something that I'm sure people on this call are aware of. But if we look, what I'm showing now is a plot. On the left is a plot of melt onset, and it's colored where red colors indicate an earlier onset, the deeper red the earlier, and blue colors indicate a later onset of melt. And the middle plot shows freeze up, same sort of thing. Blue colors indicate a later freeze up, and red colors indicate an earlier freeze up. And what you take away from those two plots is that in most areas of the Arctic, the melt begins earlier, right? As much as, say, 20, 30 days earlier. And the freeze up begins later, again, as much as 20 or 30 days later. Now, the result is the right-hand plot, which is the change in the open water period, right? Where the blues indicate a lengthening of the open water period and a red indicates a decrease in the period. And the plot is dominated by blues, with the open water period lengthening. So that has implications for weather, it has implications for surface waves, it has implications for navigation, or what people try to do, whether you run tourist boats in the Arctic, whether you try to run shipping. It might eventually have implications for fishing and resource extraction, like oil drilling in the Arctic. So these are some of the drivers, right? Why we worry about what's happening, why we worry about understanding the physics, and why we worry especially about being able to do prediction, being able to forecast what's coming in the future. So thinking about prediction, this is a plot of model results, climate models now. So really we're looking at the long-term evolution of sea ice. And let's just concentrate on the right-hand plot, which is a plot of sea ice extent in September, so during the sea ice minimum. And what you see in the black line is the actual observed sea ice extent, right? And you see this rapid decline. And then around that, sort of near it, you see a lighter gray line and a bunch of colored lines that don't quite decrease as rapidly, and then a gray area around it. And the gray area is essentially the one standard deviation line around the model results, and the gray line are the model results. I don't know if you can see my cursor. But one of the takeaways is that we're seeing a decrease in sea ice extent that's more rapid than the current models are predicting. It's within the large bounds of what the models are showing, right? This is an average of many, many models. And so the outer gray lines, these two, indicate the bounds of those model results. And so what we're seeing is not outside the bounds of what the models are predicting, but it's definitely on the fast end, very much on the fast end of what they're showing. And what that suggests to us is that we don't really understand the physics that are governing the melt, at least not well enough to improve that prediction and reduce that amount of error. So I've got the slide here again. This is something that you are living, but for other audiences that aren't quite as aware of what's happening in the north, right? There are many impacts to this decrease in ice and the change in climate. Environmental impacts, ecological collapse, right? Changes in what kinds of economic activity happen. It's large impacts on communities. It's also large impacts on industries. So there are many reasons why people should care about what happens here. Many different levels. So what does that say about the kinds of observation systems we should design, right? This is the sort of thing that I think about a lot. I do ocean physics and the kinds of tools that we use to make the measurements we need to understand what's going on at a variety of different scales. And one way to think about this is in terms of what you want the observing system to do, right? At the biggest scale, right, we would like to be able to make climate scale predictions. What's going to happen in 10, 20, 40, 50 years down the road. And we do that because we'd like to be able to help inform policy decisions, right? There's some long-term policy decisions that will get made one way or another. And it would be nice that they were backed by the best science. So the measurements you use for that they're kind of pan-Arctic. They span the whole Arctic. They don't necessarily have to be really finely resolved in space or time. So they could be hundreds of miles apart, and they could be months apart in their measurements. And the data could come back not in real time, but every year or every other year, right? And we're still fine with that. That's all good for the climate model. But at the other end are the kinds of observations we might make to tell you whether it's safe to go out on the sea ice to hunt today or this week. And at that end, the measurements are very local and very intimate, right? You want to know about a particular region around where people are living and working. You want to know about tomorrow and the next day and the week, but not so much about next year, right? So the data has to come in real time to feed those models. The turnaround has to be very, very fast. It typically has to be pretty high resolution because you're talking about limited areas and governing activity. And the shelf life of the results is not very long, right? You're really not interested in whether or not it was safe to go hunting 2 weeks ago. You just want tomorrow and next week. So that's a very different observing system, right? One is pan-Arctic, the other is very local. One has really rapid real-time data return. The other has much longer time scales associated with it. And in the middle are a bunch of more regional activities that are used to inform things like shipping, right? Or maybe resource extraction decisions on a year-to-year basis, on a shorter time scale basis. Now, the tricky part to all this, if you're doing ocean atmosphere physics, is that the systems are what we call nonlinear. They're all the scales are wrapped up together. So in order to know what's happening at the large scale, I need to know something about what's happening at the smaller scales as well, because I can't make accurate predictions of the large scales without that knowledge of the small scales. And it might be that I need the actual observations at the small scales, but if we're clever about it, we learn about the processes, the actual physics that take place at those scales, and we learn how to make a model for those that rely just on the larger scale data, so that we don't have to collect data at these minute scales to inform larger scale forecasts. But those are the kinds of worries when we think about the kinds of systems that we design to make the observations we need to eventually do these predictions. This is a plot from one of Andrea Pershintinsky's papers. And I put this in because people are usually familiar when you say, what's the difference between weather and climate, right? Weather is what happens on day-to-day or kind of a week to 10-day time scale. And it can be highly variable, right? You can have warm days, you can have cold days. You have really wet ones, you can have really dry ones. Climate is what happens at some other much larger time scale. That's a larger time scale change, right? But what do we really mean when we talk about that? In a science sense, what we mean is typically something like a 30-year time scale. So maybe several decades to make a single climate point, and then several climate points to tell us whether or not we've got a trend of some kind. So Andres plotted a number of things here. There's the time series of annual ice extent and air temperature and river discharge, right? Different markers for the Arctic. And in the solid black lines, he's got a 30-year running mean. And the yellow area around the black line, which is very wide for people who are on the phone, is the standard deviation around the 30-year mean, meaning that on top of this climate signal, right, there's a lot of interannual variability. It's not weather and it's not climate, it's natural variability that takes place at shorter scales. So just to kind of distinguish between those time scales when we talk about these things so people understand the different scales. But at the heart of this, right, are changing physics. And I put this plot up here to illustrate the range of the physical processes that we worry about as oceanographers, as physical oceanographers. They govern how the ice melts, and there's some that take place on the surface, like solar warming. There's some that, from the atmosphere. There's some that take place on the surface of the ocean, like the generation of surface waves that can propagate into the ice and break it up. And there's some that have more to do with the water column. The Arctic is kind of an upside down ocean. If you work in the other lower latitude oceans, we normally expect colder waters below and warmer waters at the top. In the Arctic, instead, it's cold and fresh on top with warmer layers, saltier layers below. And that's important because that cold, fresh layer acts as an insulator that keeps that warm water from below from interacting with the ice. So as the Arctic changes and the atmosphere gets better at putting energy into that upper part of the ocean, it can mix that warmer water up and bring it into contact with the ice, perhaps accelerating the melt of the ice from what it already is. But there are other feedbacks that happen, right? As the ice melts, it injects fresh water into the surface ocean, which is buoyant and which resists that mixing. So there are lots of different interplays between the physics that matter and that control how the ice melts and how the system evolves. And understanding those are pretty critical to our ability to understand the system and make predictions. So ONR came back to the Arctic with several major thrusts to what they wanted to be able to do. One was to be able to generate a new set of observing technologies, right? Both the technologies and the approaches, the methods for using them to maintain observations of the Arctic over long periods of time, to have persistence. The other was to really improve our basic understanding of the Arctic physics, sort of coupled atmosphere, ocean, and ice, to improve our ability to make predictions, right? To go into the development of fully integrated models that could be then used for prediction. So when we think about the observations, I think about a number of challenges we face when we're trying to make observations in the Arctic. An obvious one is that we're trying to make simultaneous measurements of the atmosphere, ice, and upper ocean, which is hard to do when there isn't ice present and very, very hard to do when there is ice in the area. We've got to resolve this wide range of timescales, right? That was just what we were talking about, was it's all kind of connected. So you have to resolve large scales and small scales to some extent at the same time. We like to be up there all the time, right? To resolve this huge range of spatial and temporal scales. It's hard to get to. At the end of the day, we're limited by the resources we have and our ability to put them out into the Arctic. So what's scalable and what's not, right? We can't do big, expensive, fancy things because they're too hard, they're too expensive, they're logistically too difficult. So how do we overcome those sorts of challenges? And the answer for many of us has been to turn to robots. Thanks to satellite services, GPS and iridium communications, and low power electronics and lithium batteries that power your phone, and your computer and Tesla cars, right? There's been this revolution in autonomous observing systems. And they are robots that range from, the slide is a bunch of pictures of different instruments, really. And they come in a few classes, things that we put out onto the ice, they either dangle from the ice and drift with it or drift on the top of the ice, right? And things that either drift in the water or swim through the water using buoyancy or propellers to push them around. But they all share a characteristic, and they're all long endurance. They last for months or years, right? They're out there on their own, they're making the measurements, they're reporting them back, and we'll talk about just how that happens in a minute. But for things at the surface, actually for all of them at this point, it's iridium satellite communications. And underpinning all of that is explosion of remote sensing, right? Lots and lots of satellites that have polar orbits, and they're all contributing little bits and pieces, or sometimes large bits and pieces, to the data stream of Arctic observations. Great data, but it's only at the surface, which is the reason why you need this combination of the robots and the satellites to give us what we want. So a quick walk through the kinds of robots that get used. This is, it's not an understatement to say this is the instrument that has revolutionized lower latitude physical oceanography and is in the process of revolutionizing biological and chemical oceanography as well. It's a very simple platform. It's a float. It's a little tube that changes its buoyancy, so it either sinks or rises. It drifts for long periods of time, typically 10 days at depth, at about 1,500 meters depth. And then once every 10 days, it does a profile from 2,000 meters depth to the surface. Comes to the surface and reports its data and goes back down and drifts again. They're, as oceanographic instruments go, they're very cheap, $20,000 a piece. They last for 5 years, so they collect lots of measurements in that period of time. And they're really easy to deploy, so people can throw them off of volunteer ships. The result is what you see in that plot, which is 4,000 floats operating in the global ocean as of last month, August 2021, with the distribution you see on the dots. And the different colors are just the contributions of different countries. But you can see they kind of saturate the global ocean, right? 300-kilometer resolution. They allow us to ask questions that were unthinkable even 15, 20 years ago, right? Because of the kinds of measurements they return. Notice one area that's blank though, right? Almost nothing in the Arctic. Almost nothing in the Arctic. If you think about why that might be, it's largely got to do with the ice, right? These modern platforms rely on satellite surfaces for a lot of what they do, and they don't have that a lot of the year when the ice is there. So this is my favorite. My team is the developer of one of the three sort of production gliders that run around the world's oceans. But this is a class of autonomous underwater vehicle, AUV. So it's a small, sort of a 6-foot long, 100-pound underwater submarine. In this case, it propels itself by changing its buoyancy. So again, like the float, it changes its volume. So it becomes more dense or less dense in seawater, meaning that it sinks or it rises. And then it controls its pitch and its roll, its attitude, to turn that vertical motion to horizontal. And so it can swim from place to place at the painfully slow speed of half an hour, 20 kilometers a day, right? But because it's so slow, it can last for a year or more out there making measurements. Typically, say 5 to 6 profiles a day, right? 20 kilometers a day, it can go thousands of kilometers in the course of its mission. These are becoming workhorse vehicles. They're not the same as the floats, right? The floats are really good at distributed things. The gliders are good at more focused sorts of things. And we've been running them under the ice for about a decade now. We'll talk about how that works in just a minute. They come in different flavors. These are different flavors of one that we develop. But just know there are two other types of gliders as well, but they all kind of have a similar range of capabilities. But when you don't have satellites, you have to do something else to know where you are. You can drift and make guesses, but the other thing that you can do is put down acoustic beacons. And if you know how GPS works, there are satellites. Your GPS receiver listens for the satellites, that calculates the distance from the satellite, And then it essentially multilaterates from multiple satellites to determine your position on the globe. And we can do a similar thing with acoustics in the ocean, where we either anchor acoustic beacons to the bottom of the ocean, or we let them drift on the sea ice, hanging from something that's drifting. The beacons emit a signal at a known time. Everybody carries a really accurate clock. So the gliders and floats or anything else is trying to figure out where it is. They wake up and they listen for the signal. On the signal is a bit of information about where the signal came from. And by calculating how long it took to hear the signal, the platform that hears it can draw a circle around the place where the signal was emitted, like you see in the bottom right-hand plot here, multiples of those. And when you've got 2 or 3 or 4 or more of those circles, you can start to calculate a position from where they intersect. Right, and it's morally equivalent to what GPS does, a lot more primitive, but it works, and it works underwater without access to the satellites. We have a similar story for communication, for transferring data, but where this works at ranges of 100 kilometers or sometimes 500 kilometers in the Beaufort Sea, the data transmission takes place at higher frequencies. So we're looking at a plot of acoustic frequency where the low frequency signals go a long way, the high frequency signals only go a very short way. So really low frequency signals like 10 hertz go thousands of kilometers. Really high frequency signals like 10 kilohertz go a few kilometers. You've got to be very close, but you can transfer a lot of data. So currently those are our limitations, right? We can transfer data when we're really close to the things we're trying to talk to, and we can navigate from reasonable distances, much shorter than GPS, but distances that are long enough to find our way around basins like the Beaufort Sea. So the other classes of platforms that we make great use of are Icebased observatories. The International Arctic Buoy Program is the oldest of those, and what you see there is a plot, shoots an old one now, 2019, of the IABP buoys that are active. They are mainly collecting surface measurements, right? Surface temperature, barometric pressure for use in weather forecasting. But there are other buoys that we put out that measure take detailed measurements of the ice that tell us how the ice is melting, right? What's happening to its strength and what its temperature is, to its profile, whether it's melting from the top or from the bottom or both. There are buoys that measure waves, both waves on the sea ice and waves in open water. Right, so a great variety of those. Another class of buoys that penetrates the surface of the ice and extends below. And those have been used to measure physical properties. The ITPs are out there in fairly large numbers. And they've collected some of the most remarkable measurements to date in the Arctic, right, drifting year round. There have been great advances from the measurements that have been made from those instruments. But also other buoys that are designed to measure biogeochemical properties, mixing, right? Attempts at much less costly buoys. The others are quite expensive and more difficult to deploy, but lighter weight buoys that do a lot less, but do so at less cost, so you can scale. You can have more of them. But fundamentally, things like gliders and a lot of the ice-based systems are costly, and profiling floats are relatively cheap. And it's relatively cheap and numerous then that we would really like to get to inform Arctic observing. So I'm going to finish here by talking a little bit about the activity itself, the work that's being done with those platforms. This is a timeline of Office of Naval Research programs, starting with the Marginal Isom, which began in 2012, went to the field in 2014, on through the current day when there's currently an experiment going on looking at sea ice dynamics, really the dynamics of the ice itself. There was an acoustics experiment that wrapped up last year, and then the Arctic Mobile Observing System experiment, which is what we're going out on for SIKULIAQ coming up. But you can see that they're marching along at a fairly steady drumbeat, with more highly likely to come. Let's see. Okay, so we'll talk about next, just without distinguishing between the programs themselves, results from 3 different programs. We looked at complementary parts of the system. The first one was the Marginal Isom program, and it was designed to look at sea ice evolution during the meltdown. So really, part of this was the idea that is, you see pictures of sea ice concentration in August in 1990 and 2012 in the Beaufort. And what you see is that in 1990, there really isn't much seasonal ice zone, right? The ice remains pretty concentrated right up to fairly close to the coast. And in 2012, there are huge expanses of marginal ice zone. So clearly a more important part of the system, right? And the question was, are waves becoming an important part of that melt? What are the processes that are accelerating that melt? What are the feedback processes? The Arctic Sea State program came along after that. Again, focused on sea ice, but this time flipped to look at the freeze-up season, right, to understand the effects of changing sea state on the autumn freeze-up. And then more recently, the program that we're in analysis on right now was the Stratified Ocean Dynamics of the Arctic Ocean Program, SODA. And that was really aimed at looking at the upper ocean, at the processes that control stratification and delivery of heat from the ocean side. So again, it's still kind of all about the sea ice because it usually always is, but this is really more focused on the upper ocean's role in governing that and its role across the annual cycle. So you can imagine those imply different kinds of observations. What you see here is a cartoon from the Marginal Isom experiment, which does a pretty good job of describing what was done with the instruments. There were roughly 100 assets deployed, 100 different instruments during this experiment. So lots and lots of individual installations. And the idea was to put a carpet of instruments down, ranging a few hundred kilometers from south to north, across the ice during the spring when the ice was still solid enough to land aircraft, doing it all from aircraft, with the idea that as the ice melted out, you would always have these measurements that went from open water through the marginal ice zone deep into the pack. So there would be this ability to contrast conditions in those different environments. Some mobile instruments like the gliders running in between those two areas, and then some fixed instruments that are in the ice and other instruments that would be mostly outside. So the first thing you see is the use of we saw all these robots individually, and now you see how they're used as a system, right, to cover each other's weaknesses, to measure different scales and measure different properties, to form this integrated system to make the measurements we want. The kinds of things you get out of that. This is a picture following the sea ice now, so it's in the ice frame reference. It was taken from a couple of instruments that were mounted on the ice. And really the goal here was to take a look at the evolution of the sea ice and try to decide how much of it, how is it melting? Is it the surface air temperature? Is it melting from below because it's getting lots of heat from the ocean? Is it melting because the waves are coming in and breaking up the ice and causing it to melt faster? And the answer was, when you looked at the picture, that the dominant source of melt was the air is warm and the ice melts from the surface, right? The Arctic is warming faster than the rest of the globe. That warming is causing accelerated melting of the ice from the surface. Next comes basal melting, or melting from the bottom, right? And that's something that the SODA program is focused on, is the delivery of that heat and the feedbacks that may either accelerate that or dampen it. But in this case, during the Marginal Isom program, what they saw was that there was definitely delivery of heat from the bottom, and they saw significant basal melting, just not as big a factor as melting from the surface. What we didn't see was waves. We didn't see waves breaking up the ice and accelerating the melting as we had expected we would see. So that's not happening yet in this case. And then we see some other processes like the meltwater forms this halocline, right? It's fresh, it's cold, but it's very, very fresh. So it's very light. It sits on top of these warmer waters, and then that damps the mixing of these warmer waters into the surface layer. So it damps that delivery of heat from below. You see kind of cool things if you look at high resolution sections. These are sections that were taken by the glider during meltout and during freeze up across the ice here, right? So you can see the gliders crossing the marginal ice zone in these remote sensing images. So you see structures like eddies at the edge of the ice. You see very sharp gradients in temperature and salinity that are associated with the ice edge, and changes in the subsurface heat storage. And then in the freeze-up period, we saw what looks to be a secondary bloom. We're still working on this, but it looks like it's probably associated with elevated mixing. As things kick up at the end of autumn and you get some convective overturning, so the waters get cold and they go and they scoop up water from below. That water has more nutrients in it. There's still just enough light to let things grow, and so you get a little bit of a phytoplankton bloom during that time. Things that you see by being out there over the long term. These are some measurements that Jim Thompson and his group made during that period of time. But the point here is looking at the role of waves in the marginal ice zone. And to simplify things, let's just look at the right-handmost figure where you see that things are either colored in orange or they're colored in blue. And the top panel is a wave spectrum, meaning it's the amount of energy that are in the surface waves. And it's plotted with high frequencies on the right-hand side and low frequencies on the left-hand side, meaning that the low frequencies are what you think of as swell, really long period rolling waves coming into the ice. And the high frequency waves are things you might think of as chop, right? Much shorter waves, much shorter wavelengths, much shorter time periods. And what you see when you look at that is a spectrum that looks relatively normal, open water normal in the orange, in the open water. But when you come into the ice, you see a huge reduction in energy at the higher frequencies, but not a very big reduction at the lower frequencies. So the swell is still making it into the ice, but there's not very much of it. And the higher frequencies aren't making it into the ice at all. And that shows up in the mixing as well. The lower panel there is turbulence in the very surface layer in the upper couple of feet. And you see that there's a fair amount of turbulence mixing in that layer when you're in open water, and it damps fairly quickly when you're in ice. So waves not having a large impact during the melt period and accelerating the melt. But we also make detailed measurements. This is from SOTA, and it's the work of Sam Brenner, who's one of the graduate students in our group. Sam has been looking in great detail at measurements made from moorings. So these three stars that you see in the plot, right, that are in an area that is ice-free during the summer, an area that's in kind of the marginal ice zone during summer, and an area it's pretty much ice cover most of the year. And the question Sam was asking was, we have these parameterizations, like I said, we'd like to try to create models, if you will, for processes that we can't afford to resolve routinely in observations, right? Maybe we can resolve something in satellites, like in this case, ice concentration, sea ice concentration. And we would like to relate the sea ice concentration to the bottom roughness of the ice, because if we can do that, we can make models of how the atmosphere puts energy into the upper ocean through the ice, right? We need to know something about that roughness to understand how that transfer works. And that transfer is important for understanding how much mixing there is, how much momentum, or how the atmosphere pushes the water around, right? Sets the water column in motion. So Sam is asking questions about, well, how would those parameterizations really work? Or what would I really have to know to get the drag right? And the answer is, he divides it up into different components of the drag: skin, keel drag, flow edge drag, right? You can see the plot at the top there. But when he looks in detail, he finds that sea ice concentration is really not a very good way to estimate the bottom roughness. Doesn't do a very good job. He finds if he knows something about the geometry, right? If he has measurements of the actual geometry of the bottom, he can make pretty accurate measurements of the drag coefficient, right? And so that's an unfortunate story, because it says that better measurements are needed. We can't get away with the ones that we can get from satellites, at least not that level. But those are the things that we like to know from these kinds of observations. And there you can see how little process measurements scale up to matter to much larger kinds of models and things that we want to know. So that's a reason why we focus on little tiny things to get to the bigger things we want to be able to model or predict. So last, I just want to show another model of how these things are used, right? This is the SIKULIAQ. Jim McKinnon and Jim and Harper Simmons and Tom Peacock went out, and they were really interested as part of SOTA in looking at the role of the Bering Strait inflow, which carries a lot of heat into the region. And there are questions about how that heat gets delivered, how it goes from where the bearing enters. It spreads out over the shelf, right? How does it make its way into the deep basin? And there's been a lot of previous work on this. So this is not news. This happens, and it's not news that the water gets off. But they did want to try to understand what some of those mechanisms might be, or make another step in that story. And one of the ways they did that was they took SIKULIAQ out and made measurements from the ship like you normally would, but they brought with them a large pile of robots, which they then distributed from the ship to essentially increase the footprint of what they could do from the ship. So you imagine like an aircraft carrier, right? You go out, you put out a bunch of robots, the robots work, they make measurements, and then you come back and you've got both the measurements the ship has made, plus the much larger footprint of what the robots have done. And in many cases, you leave some of those robots behind so that you get not only a better footprint in space, but a better footprint in time too, right? So they're still working at this data, but one of the things that they're trying to do is go from the kind of bulk views that we've had to date of the sort of smooth spreading of Pacific water as it comes in through the Bering Strait, to get observational measurements to support ideas like people like Mike Spall and others have been pursuing of, is this water taken off in eddies that are spun off of the shelf, or does it come off in filaments that are spun out of canyons, right? How is it subducted and how is it brought offshore? What they saw in an individual snapshot was a really warm filament of Bering seawater that came up over the shelf and then peeled off, headed offshore, and slipped under the colder but lighter waters offshore. So we call subducted, right? It went underneath that layer, and they're looking at questions. Okay, we've seen one instance, right? What does that mean? How often might that happen, and how big of an impact might that have? I threw this one in here just as an example of what you get if you make measurements over long periods of time in places. And this, right, this is ITP data, of which there are many in the Central Arctic, and data from another platform that was used during SOTA. But the interesting thing that they saw here, these are drifting in the Central Beaufort in midwinter, really. Whoops. And what they saw were several instances of heat injection from 40, 50, 60 meters up into the surface mixed layer of the ocean, for reasons which we don't yet understand. But they're present in the data, and they're present enough that they're not simply flukes. They're just a little phenomena that we neither understand the physics nor the potential large-scale impact of that yet. But that it happens is interesting. So I'm going to conclude with this little cartoon here. And the cartoon is from the Arctic Mobile Observing System, or the AMOS project. AMOS is the name kind of suggests, is really technologically focused. And the idea was to put together some of the advances that we've made in autonomous observing over the years to see if we can develop a mobile, relocatable, scalable system for making Arctic observations. So it's a combination of acoustic navigation nodes, right, and communication nodes, also with an attempt to make them recharge stations. So like a recharger for your electric car, right? These are floating rechargers for autonomous vehicles. They might run in the ocean. And we run two classes of autonomous vehicles. The gliders, which I've already talked about, which are long endurance, they run on a primary battery, so they don't recharge. And they wouldn't be capable of using one of these recharge stations because of the way they navigate. But there are also faster, more capable vehicles that get run, autonomous underwater vehicles that are propeller driven. They can carry heavier payloads, they can go faster, cover more ground more quickly. And those do need recharge. So the idea is to be able to do that from some of these stations. And then using profiling floats on a variety of ice-based observatories as well in these configurations that you see kind of in this cartoon. So we're currently testing various elements of that system. and we'll be testing them for the next few years. Then we'll hopefully have a full-on systems test in 23, 24. But that is the goal, to be able to use this to make more persistent observations of a large number of variables, and to be able to do so in a wider range of environments in the Arctic. So I'll leave you with that summary slide and answer questions. Thank you for listening.
All right. Well, thank you so much. Thank you so much, Craig. I'm going to see, you might want to take yourself out of presentation mode or screen share, I guess. There, so people can see you. Thank you. Holy cow, for making those slides understandable for someone like myself. So I have a better understanding now of sort of the what it is you're trying to get at with the physics, and also the future with the robot scenario. That's wonderful. We haven't seen some of those. I haven't heard about all those equipments, but the fact you could charge underwater, pretty interesting. Anyway, first off, I forgot to mention for everyone, there is a chat feature at the bottom of your, if you're unfamiliar with Zoom, there's a chat feature down there. It looks like a little cartoon bubble, and you click on that, put some love in there right away for Craig Lee. He's giving this talk from Seattle. It's late for him, and he has taken the time to let us know about what his plans are and all of that interesting stuff going on in the Arctic. So thank you, Craig, for that. And we have a great audience. They're very good. I have some questions for you, but I better throw it open to everybody else first. So any questions or chat questions for Craig? Oh, you're even getting claps. That's nice. Thanks, Marina. My question is, what actually physically, how do you get that buoy to go up and down for 5 years? Is that just like, how does that work? Or is that a secret for you know, you can't give it away, a secret? Is that chemical or compressed air? I mean, how does that?
Yeah, it's there are a couple secrets. The vehicle itself runs on it has a swim bladder.
Okay.
And it moves oil between that swim bladder and a reservoir inside the pressure case. So it doesn't have to change its volume. And it's not much oil. It's about the size of a Coke can. So that's how it drives itself. It manages to have long endurance because it has a massive number of lithium primary batteries. And we are insanely stingy about how that energy is used. The vehicle spends most of its time pretty much completely asleep, wakes up to do things and goes back to sleep again, with an amazingly stingy duty cycle. And it moves really slowly. So it turns out that the drag is quadratic, so it goes up really quickly with speed. So if you go slow, you can go for a long period of time. If you try to go fast, not so much.
Right. Thank you for that. Still, you're getting kudos in the chat box. And my other question was, maybe this is novel, not novel to you, but it's kind of novel to me. And the ONR, which you were mentioning several times, is the Office of Naval Research, for those who may not have been familiar with that acronym. And we certainly, if you live in the Bering Strait region, we understand military and living on the border. In fact, I was going to say one of your impacts you should include under the changing environment would be impacts ecologically, industrially, and militarily. So even here in the Bering Strait region, we're seeing the effects of some of that. We're having a NORAD drill right now this week. So we have F-22s that have been seen in Nome, and we understand that there's a lot of other things going on, but we're glad you're getting a handle of it. What is interesting to me is you're talking about the transfer of data underwater from your machines to those, is that correct? Those buoys or anchors or?
Right.
So that's pretty magnificent. If you can get So from a science perspective, that's awesome because you can have your instruments underwater all the time and then you can beam out, I suppose, when you're ready. You fill up your
Well,
machine. What is it?
it's all done with acoustics. And the problem is you have to be very close.
Ah.
Right? In order to move, you don't have to be that close to get a signal to calculate your position. Right, those signals are very low frequency and they can go quite a ways. And you don't need a lot of strength, right? They can be a very weak signal to be useful. But to calculate, to transfer data, right, it has to be a higher frequency signal so you can encode more information on the signal. And the higher frequency signals don't go very far. They go a few kilometers. So you either have to have a platform that can swim to one of the nodes to talk to it, or you have to get really lucky. And it's a big ocean, the platforms are really small, so you have to get really, really lucky, right, to have a chance encounter.
Right.
Allows data transfer. It's really got to be very intentional.
Will that change as the time goes on? You sort of had those, I can't think of the name of it, the buoy thing that goes up and down that's revolutionizing and just covering the oceans, but is very few in the Arctic. Is
Yeah,
that
so
sort of the future, is to bring that sort of thing and then have the ability to transmit information up through the ice so that we know what's going on?
I think that's definitely the future of Arctic observing at the climate policy scale and probably at the strategy scale. And the reason why I say that is that we're almost there, right? We're almost to the point where we can do it. I'm hoping we're going to try soon. But we can't get the data out reliably in real time. Right? We can only do that when it's ice free. And so there's a latency to that data delivery that's probably unacceptable for some of the more near-term uses.
Oh, I'm going to mute. Jared, I'm going to mute you. We can hear the music. Okay.
But yeah, we're chasing other ideas for how to move data around more rapidly. You know, those will all cost more. They'll be more complex to do. But that's probably okay because the places where you want to do it are more confined. Where you don't need to do that everywhere. You just need to do it in places where it matters to people. So
you do have a question in the chat box, and that is from Marilyn. When it's asleep, that would be your
yeah, I see it.
Is it neutrally buoyant? When it's
No, so it's actually so like driving blind. The vehicle goes to sleep periodically, and it does so while it's actually navigating. So if you think about moving at half a knot, it's very, very slow, right? And you're kind of moving through the water at that speed. You might wake up and check your compass and verify that your nose is pointed in the right direction, and that at the depth you're at, you still want to keep diving or climbing, you know, whatever you're doing. And then maybe you go to sleep for 10 or 20 minutes, right? And keep the vehicle's doing whatever it was doing. It's still diving and still moving in the same direction. Because you know that in that 20 minutes, you're not going to go too deep, or you're not going to go past your waypoint. Right? Then you wake up again and you check again and so on. So yeah, it keeps going.
So sort of like sleeping while you're driving a little bit. Yeah. Just when you get to your destination.
Cat naps.
Cat naps. Perfect analogy. Cat naps while it's underway. Let's see. Is there any data that you'd like to record that is not currently being done? Thank you, Matt Caps.
Lots, really.
Lots, did you say?
Lots.
Lots, okay. So,
right, I'm a physical oceanographer, and our measurements are pretty easy. We measure temperature, salinity. We have sensors that will do that, and they're relatively cheap and they're relatively reliable. But things that we don't do so well, right? We don't do autonomous atmospheric measurements very well. in the boundary layer, and those are really critical. We can't put a weather station out in the middle of the Arctic and expect it to last all year round. Make the measurements we need, and those are super important. And yet we're still struggling to figure out how to do that. We don't do measurements of ecosystems or biogeochemistry very well at the same scales, right? They're very intensive to do. The measurements that are made are great, but they take a lot of work, and thus they can't be made at the same scales, right? The same time scales and same space scales you can make physical measurements in. In an ideal world, we would be able to make some core set of those measurements all at the same scales and kind of make sense of the system together. So I'm hoping we'll get there one day, but it's right, lots of smart people working at it.
Last question. Any of your instruments go, I don't know, maybe there are more questions, so I shouldn't be saying that. But any of your instruments going in the northern Bering Sea, Bering Strait region?
No.
Or can you not tell us?
Yeah, no, everything we're doing is further north.
Okay, well, we're missing out then.
Beaufort, yeah.
And you were saying that you were hoping to get to with SIKULIAQ, you're going to be here in a week, and you were going to board SIKULIAQ and then head up north. And we hope you are all safe in your transit through here. We used to worry about travelers, but now because we thought you were bringing it, but now I worry for the travelers because you might get it, the COVID. So things have really changed here. But when we see the ship, we're gonna not, sometimes in better days, we've had open houses and things like that, but we're going to let people know that not to go down to the ship at all if you can avoid it, just because people will be worried about that. And you're hoping to get to very high north, and I was telling you it's been cold here. Craig and the SIKULIAQ are hoping to get up to what, 78 or so. Yeah. That's quite high north. We wish you luck on that.
Got one more question in the chat box, I think.
Oh, yep. Thank you, Marilyn. Could you talk a little about the devices that use frequency and sound levels that might harm marine mammals? Is it only for data transfer that higher frequencies are needed? Good question. Good question.
No, excellent question. So the frequencies that we use right now, we use 900, 35, and 10 kilohertz. The duty cycles are quite short. So for instance, the 900 hertz signal is, what is it right now? About 60 seconds, 6 times a day. So basically 6 minutes every 24 hours. We do modeling studies for all of these to try to understand what the sound propagation is. And the acoustic studies that were listed earlier also made measurements of the actual sound propagation to try to understand how far those sounds get. We don't believe from the data and from the modeling that the levels are such that they would harm marine mammals. The high frequencies really are only used for data transfer. And right now we do almost none of that. Even when it is done, right, it won't be a common thing just because it's expensive from an energy standpoint. So it's harder to do. One thing that we are hoping to do in the coming year is to put out acoustic recorders for marine mammals on the central Beaufort moorings to give us a better idea who's there. And then we're actually talking about trying to put a couple of receivers over the slope shelf region, just to monitor what signals are doing.
Great. And actually, I made a mistake and skipped over Anatoly, who has a question. Welcome, Anatoly. You also mentioned the importance of measuring the ice bottom roughness. That came after your, are there any data that you'd like to record that are not currently being done?
Yeah, from a process standpoint, we've made stabs. There's a device called a multi-beam sonar that characterizes the ice bottom roughness in the swath, and it's typically run from things like autonomous submarines, right, or actual submarines. We've tried to do that for moorings unsuccessfully so far, but hope to try that again. right? That would be one way to get at those measurements. But there'll be, it'll be hard to do that on a routine basis. The instruments are expensive and they're kind of finicky. So I think our hope is to find a way to get at that parameter using a proxy, if we can. Or maybe we won't be able to, and we'll have to figure out a better way to collect those measurements. But it's a hard one to get, absolutely.
All right, and there's another comment from Marilyn, deployment of PAMs. And I'm hoping, Marilyn, you can maybe type in what PAM is, or.
Passive acoustic monitor.
Ooh, she must know what she's talking about there. PAMs would provide very welcome and needed information. Hope it happens. So well done.
It's in the planning for next year.
Wonderful. And you were also saying we'll see you next year on SIKULIAQ, also coming north, and maybe we can hear next year about how your work went this year. Hopefully you have a very successful cruise. Tough time to have a cruise, but we wish you the best.
Thanks.
Yeah, we're counting on you. I think a lot of people are counting on you actually to get up there. So
yeah.
We wish you the best. Any other questions or comments? Again, thank you for all your comments to Craig for showing him a little love from Nome and the Bering Strait region. Does anyone on the phone have any comment or last minute thoughts? We want to make sure. It's very difficult to be a caller on a Zoom call, and you've stuck with us.
Yeah, I apologize for not getting those slides out earlier. I read your email more carefully, Gabe, today, and I realized that in that email was the plea to send the slides early so you could send out the resolution versions, and I just totally spaced it.
That's okay. We are a dedicated bunch, and the Bering Strait is very flexible. And but thank you very much. Next time. All right, you got a clap for mentioning that, so well done. Oh, that was Jackie and Lee. Well done. Full confessions, always welcome. All right, so Craig, let us know when you're underway, and we will be standing by to help assist you in any way we can, or your science party when you come through Nome. Again, we won't be seeing much of you, and hope you can just shuttle right into the ship and lock up tight.
Will do. Thank you. And yeah, hopefully next year we can do this in person.
We look forward to it.
Right.
And with that, thank you so much.
Thank you. Thank you.
Take care, everybody. Thank you for listening.
Okay. Good night.
Good night.